Yeah, okay. Hello everyone. Welcome to the sixth talk of this season's Isogeny Club. Uh, this is not the Isogeny Club. Before we get started with today's talk, I just want to remind everyone that there's no talk in 2 weeks because of Eurocrypt happening, and in regards to that, I also we should again plug our affiliated events, which we're all really looking forward to. At the brainstorm sessions, and where we hope to see all of you there. Also, submission of ideas is now open, so please see the separate email which from a few days ago, or let us know if you haven't received an email, which explains how to submit your ideas, which we're looking forward to as well. All right, enough of the chit chat. We're here to see Valerie's talk today. So today we have Valerie Gilchrist giving a talk. She is a PhD student at the University of Brussels. And yeah, take it away, Valerie.
Thank you. Thank you both for having me. I'm very happy to be here today. And today I'm going to be talking about how to compute rational isogenies with irrational kernel points. This is joint work between Gustavo, myself, Anael, and Ben. It's a project we started sometime last summer. We've kind of been working on a little bit here and there since then, and finally it's kind of coming to a wrap. And the ePrint will be out very soon. But yeah, so at any point in the presentation, please feel free to interrupt me if you have any questions, comments, etc. Or if you put something in the chat, I think either Kine or Jonathan will kind of yell it out for you. So yeah, getting started. So starting with separable isogenies, these are very nice to work with, as I'm sure most of us know, because of this property that they're defined uniquely up to isomorphism by their kernel. So when dealing with siglet kernels, what this means is that the isogeny can be defined by just one point, namely this point that is generating the kernel group. And of course, these pop up in most isogeny-based systems like Seaside and CRS, kind of a super singular and an ordinary example. And ironically enough, the main motivator for this work was to improve CRS. So for many of you, probably, if you're new to isogeny crypto, then you might have started by learning kind of what CRS is, and probably very quickly discarded it as not being kind of feasible for real world use. But kind of the main drawback for CRS is that it's so slow. And the reason for this is because you're doing these computations of isogenies that have irrational kernels, which we'll get to in a moment. But yeah, so if you are curious about CRS, kind of the state of the art, there's this paper by Luca De Fea, Jean Kiefer, and Ben Smith that kind of looks at how to improve it a little bit more. But when this paper came out, it was actually around the time Seaside came out. And so kind of more people turned to Seaside as an alternate. But maybe let's work like this and kind of further improvements. CRS maybe one day could be close to feasible, who knows? But yeah. So going back to these irrational kernels and what we mean by this. So kind of the context or the problem we're setting up is that we want to compute this isogeny of degree L, whose domain is this curve over some field FQ. Usually to define such an isogeny, to use things like Vélu or the formulae in Coel's thesis, you're going to look for a point of order L, and you're going to use this point to generate your kernel. And this will lead to your isogeny of degree L. Now, suppose that you can't find such a point over your base field. So in order to find your point of degree L, you actually need to go to an extension field. That means that the group generated by this point, let's call it P, is what we call irrational because it's not on our base field. That is, if you were to build an isogeny from this point, you're going to end up with a kernel that is over the base field, but whose kernel points are not. And then in the case of Vélu, when you're trying to run these rational equations, it's going to ask you for the kernel points. But because in our instance, these kernel points are not over the base field, they're over the extension field, you have to do all of your arithmetic over the extension field. And this is what's really going to slow you down and make things really costly, really slow. And this is kind of the main crux of CRS. So in this work, we're going to look at ways to kind of improve this and make this a bit more palatable, let's say. So getting to kernel polynomials, Vélu's formulae and also these formulae from Cole's thesis are going to use this thing called the kernel polynomial several times. So we're really going to focus on how we can evaluate this polynomial in a nice way. So I've written here kind of what the polynomial looks like, d of x, and it's this product using these points from this set. So the way it's written, we're assuming here that P is the generator of the kernel and S is the subset of the multiples of P. And the way we want to choose the subset S is that basically we want all the multiples of P without the identity up to negation. So that's to say, if we already have P in our set S, we do not need minus P, or vice versa. If we have minus P, we do not need P. And the reason for this, as you can see in the equation, is that we're only concerned with the X coordinate of P, not the Y coordinate. And all negation does, all negation does is change the Y coordinate, but it preserves the X coordinate. But so yeah, so to define this kernel polynomial, we're very concerned with the set S. And then again, reiterating, because P is in our context being defined over an extension field, D will not always split over the base field. In fact, it will not if we're working over an extension field, but the coefficients will be defined over the base field. That is, the kernel will be defined over the base field. So looking at an example, we're going to take L to be 13 and K to be 3. So that means the point we're working with is order 13, but it did not exist in our base field. So we had to go to E of F cubed to find this point. We're concerned with choosing the set S. So a subset of the multiples of P without the identity up to negation. So here we have all the multiples of P without the identity. And some classic examples for choosing the set S include choosing just the first half of them. So here you can see we don't have the negatives of the ones we've chosen, just going from P up to L minus 1 over 2P, or also choosing the odd multiples of P. Either of these are kind of standard choices of S. In terms of cost, taking, for example, if we're just taking the first half of all those multiples of P, we're assuming we already have P, so we're going to use 1x double to get 2P. And then for each one after that, we're going to use 1x add, basically adding P one time at a time, once at a time. Okay, so this is kind of what we're comparing against the standard. The first improvement we're going to look at is kind of like a neat thing you can notice. So we're going to take all our multiples of P and we're going to rearrange them in this kind of fun way. And so maybe take a moment and try to decide for yourself what is special about this arrangement. And maybe looking at those first 4 multiples of P, it will be an indicator that each time we're just multiplying by 2. And in fact, yeah, the last one, 7P, when you multiply it by 2, gets you 14. Modulo 13 is 1, so it just kind of starts over. And then when we're choosing our set S, this means we would just need the first half of this arrangement. And we've done this because now to get each one, we're just doubling, doing 1x double each time. So kind of the natural question is, well, it worked in this example, but will it always work? Right? This worked because we're working modulo 13. And so it worked in this example because each of these multiples of P can be written as a power of 2. And so, will this always work? Let's see. So first, to formalize, we're going to recall this definition of what a primitive root is. So we say n is a primitive root modulo L if every a co-prime to L can be written as a power of n. So in that previous example, we had that 2 is a primitive root modulo 13, which is why we were able to do that arrangement where we're doubling each time. So from this, we get this lemma that says, if 2 is a primitive root, then we can choose our set S to be kind of these doubles all the way through. Now, in the paper, we do go make this a bit stronger in that if 2 is semi-primitive, meaning if 2 has order L-1/2, with some additional constraints on L, it'll still work. But for the moment, we're just going to focus on the primitive case because it's a bit more elegant. But yes, so this is kind of what we'll refer to as the doubling method, etc. So exactly how often does this happen? Like I said, you need 2 to be a primitive root. So will this happen often enough to kind of make it interesting? We think yes. If you look at all of the primes between 3 and 10,000, around 57% of them are either primitive or semi-primitive and satisfying the constraints, additional constraints you would need. Here we've listed the primes between 2 and 600. And you can see kind of that top row is the ones that meet our requirements, and the bottom row are the ones that don't. And in bold, we've put kind of the C-size 512 parameter set just for a bit of context. This does kind of raise an interesting question to do with C-side, in that in constant time C-side, which is C-side, or even I think kind of the fastest known way to do C-side, I think, I'd have to double check, but they use this method called batching, where when they're computing these isogenies, they're going to do it kind of in batches of them. And so naturally, with the batches at the moment, they're going to choose the degrees that are closest together because you have to take the maximum of that and assume they're all. So like you would take a batch of like 3, 5, 7, but you'd compute them all as if they're 7 isogenies with dummy operations to make it constant time. This would provide kind of a different way to choose your batches, in that you could choose them so that the batches all have like primes in the same batch have 2 being primitive or not. We haven't explored this yet, but this might be an interesting problem at some point to see how much of an improvement you could get just from this doubling method, and if it was worth kind of changing the batching criteria. That's something to think about. And then looking at cost, so looking at exactly how much improvement we do get. You'll recall from kind of the standard method where we just took the first half of the multiples of P. This cost us 1 double and L-5/2 adds. And in our doubling method, it was L-3/2 x double. So first looking at kind of the cost of an x add versus an x double, and maybe focusing on the Montgomery model, we have that an x add is going to cost us 4 multiplies and 2 squarings, whereas an x double is going to cost us 2 multiplies, 2 squarings, and a curve operation. So here, the important thing to note is that multiplies and squarings are being done over the extension field, whereas the curve operation is only being done over the base field. So in terms of how these kind of compare to each other, if we think of kind of the worst case for us, and in our case is when k equals 1. So when you're not even going to an extension field, then the multiplies are being done over the base field anyway. So you could say it multiplies around the same as a curve operation. So in this case, an x double is only saving you 1 multiply each time. And this will kind of sum up to around a 16% saving. Although it is worth noting, even in the k equals 1 case, if you're starting kind of on like a well-chosen starting curve, then this Montgomery coefficient could be quite small, in which case the curve operation is going to be quite cheap. But if you're like taking a walk in a random, you're taking a random walk in a graph, then you don't really have any control over what that Montgomery coefficient is going to be. So the curve operation is going to be a lot closer to a multiply, in which case you get the 16% savings. So the best case for us, though, is when we're going to be working over extension fields, because this means that the multiply being done in the extension field is going to be way more expensive than a curve operation being done over the base field. So if you look at something like k equals 11, that multiply is going to be at least 11 times more expensive versus the curve operation. So kind of going to higher extension fields will make this a lot more appealing. Okay, so looking at the next improvement kind of that we wanted to apply, we wanted to try to take advantage of Frobenius and how this might act on our points. So again, we're in the same context. We have this point of order L that's defined over some extension field. And in particular, we're assured that this is kind of the smallest extension field that contains such a point. So no subfield, no proper subfield containing FQ will have a point of order L. Then we have that the subgroup generated by P is going to be Galois stable. So for us, this means that Frobenius is going to act as an eigenvalue lambda. So instead of applying Frobenius, you can do scalar multiplication by lambda. And the same for composition. Instead of composing Frobenius twice, applying it twice, you can just multiply by lambda squared. To find lambda, it's going to be non-zero, and it's going to be an element of order k in the multiplicative group of integers modulo L. So again, we're going to look at an example. So going back to the same one, L is 13 and k is 3. So we have our point of order 13, and we found it in the subfield FQ cubed. So here we have Frobenius is acting as an element of order 3 modulo 13, meaning it's either the multiplication by 3 map or the multiplication by 9 map. To make things easy, we'll suppose it's a multiplication by 3 map. So now, again, we're going to see how we can use Frobenius to choose our set S. So we're going to rearrange it in this kind of funny way. And maybe you want to take another moment to try to figure out for yourself why we've arranged it in this way. But looking carefully, maybe you noticed we have some very nice behaviors going on using Frobenius. So looking at kind of this first bubble, or what we're going to call orbits, we have that when you multiply by 3, p by 3, you get 3p. By 3 again, you get 9p. 9 by 3 is 27. Modulo 13 is 1. So Frobenius is just permuting the points in this orbit. And the same for each individual orbit. And if you look very closely, you'll also notice that the orbits are kind of preserving negation. So the negative of one orbit is exactly another orbit. Meaning for our set S, we can just take 2 of these orbits where they aren't each other's negative. So if we take these first 2 orbits, that would be enough for our set S. To generate each orbit, you can take any points out of the orbit. But now we kind of want to think of how do we want to choose the generators of the orbit? Is there kind of a nice way? And the way I've written it here is, again, meant to be a bit implicative. Maybe take a moment to think of what's going to happen next. But yeah, you'll notice we have P, 2P, 4P, 8P. We're doubling again. So just formalizing what I just said, basically we're going to choose this smaller subset S0 to be the generators of our orbits. And then once we have these generators, we're going to apply Frobenius or kind of multiplication by lambda, roughly k times, and this is going to get us our set S. We make this distinction between k being odd or even because the Galois orbits are going to behave a bit different. But this is more or less the idea. And so again, in terms of how we want to choose our orbits, we're going to try to use this doubling trick again. So we get this lemma that when 2 is primitive modulo L, or some other conditions to do with being semi-primitive, we can choose this set of Galois orbit generators to be just the first few doubles. And so here, kind of we look at the example we were looking at before, where L is 13 and K is 3. We get exactly that we're going to range I between 0 and 1. So we have P2P, just as we saw before. Cool. And now looking at how we can actually use this in our kernel polynomial, we're going to do a little bit of math, but I promise it's not too bad. So this is our kernel polynomial that we started with before. The idea here is that we're going to, for each generator of our Galois orbit, basically just generate the orbit. So we're going to take our generator and then apply Frobenius however many times we need to complete the orbit. And we do this for each generator. Frobenius is just Q with powering, so that's fine. But then we can kind of rearrange the order of products to make this even a bit faster. In that instead, first we will find what this product is using all our Galois orbit generators. And then once we have this value, assuming if you're evaluating a point over the base field, then you can pop out kind of, since we're working characteristic Q, pop out all of these Qth powerings to the outside and you get this nice sum. I think in the paper, we do this a little bit different, kind of using more of the eigenvalue stuff, but this is the idea behind it. This is also a good point to point out, if you remember from a couple episodes back in Isogeny Club, when we were presented Urine for the People, they also touch on kind of kernel polynomials using irrational points, but their main focus is fully computing that polynomial. So they really store the whole thing, whereas we're more focused on just evaluating it at points. So by evaluating D naught of alpha first, you'll see we never actually have all the kernel points at once. We're just using these Galois orbit generators, getting what this value actually is, and then just powering it at the end. So it's a bit different. And this is also why when we were thinking of kind of what to compare to see improvement results, we decided to take this algorithm due to Costello and Heath-Seal in 2017 as a basis for comparison, because they're also more focused on evaluating polynomial and not just computing it. So kind of looking at what they did, they derived this affine formula. They kind of projectivize it, and from this, they get the rest of their algorithm. If you're curious about the details, I will refer you to their ePrint. This was kind of intended for use in SIDH, but it has applications outside of that as well. And they go into this in the paper as well. And they do a few other things. And then this work is later kind of generalized to the even case also by Jaus-Gens. Sorry if I butchered that. But yeah, so this is what we're comparing our results to. In terms of the comparison, we decided to count how many operations we're using. So we're counting multiplies, adds, and squarings being done in the extension field. These are very preliminary results. We're still finishing up the ePrint, so like the work is not completely finished yet, and we want to still do a bit more analysis, but just a few examples for a bit of comparison. You can see we have a few different L values, a few different K values. We're getting quite a bit of savings in terms of multiplies and adds, probably close to 90% for each of those, but at the cost of quite a bit more squarings. On average, close to like 50% more squarings, but you save quite a bit of multiplies and adds. So also worth noting, this is for K bigger than 1. When K is smaller than 1, it's still similar patterns, but not kind of to the same extreme. And also 2 is primitive. So we're using this doubling trick each time. Okay. So now the main focus of this work was evaluating the kernel polynomial, and that's kind of where the most savings will come into play. But we did decide to also tackle this problem of actually finding a way to compute the kernel generator. So in this context, we're looking for this point of order L, and we're assuming it exists in this extension field and not any proper subfield of it. So starting with kind of the standard approach to finding this kernel generator, the first step would be to sample a random point from the extension field. Our next step is to multiply by the cofactor. So the number of points on the curve over L. And the reason you do this is because you're kind of forcing it now into the L torsion group. So this new PL will have either order 0 or order L. If it has order 0, you just start over with a new random P. If it has order L, you're good and you can use PL now. So to look at kind of our improvements, we're going to start with a couple of examples. So starting with K equals 3, we notice that we can write E over FQ cubed as this direct product. So we know that E over FQ is a subfield of EFQ cubed. So we're going to write it EFQ direct product, some other stuff, H3, kind of the rest, the leftovers, if you will. And the reason we do this is because, like I just said, we're assured that no point of order L exists over E of FQ. So we know that the point we want, or the point really where we want to be sampling our points, is from H3. And so kind of the question is, well, how can we sample points from H3? And so we go back to using Frobenius, of course, love Frobenius. And so the idea is that, well, we know Frobenius is going to fix points on EFQ, just like Frobenius cubed will fix points on EFQ cubed. To generalize this, we know that Frobenius fixes, like Frobenius I Howard will fix points over E of FQI. So this map, Frobeniusly I minus 1, its kernel is going to be all of the points in E over FQI. So the idea is that if we apply this kind of in the I equals 1 case to our point, then it'll kill off the subfield part. So putting this together, what we're doing is we're sampling this point, this random point P from the entire extension field. We're applying this Frobenius map to kill off the subfield part. And now the thing we need to multiply by to get it to the L torsion group is smaller, because H3, the cofactor you're multiplying by, is going to be smaller than the previous cofactor. So in this case, we save about 1/3 of the multiplications. Not bad. Looking at another example, gets a bit more complicated. Actually, maybe I should go back and ask if anyone has questions here, because it'll get a bit more complicated in a second. Okay. So looking at the k equals 6 example, it gets a bit more complicated because we have more subfields involved. We see, again, we have EFQ as a subfield, but we also have EFQ squared as a subfield and EFQ cubed as a subfield, because 2 and 3 divide 6. And so again, from before, we know that this map, Frobenius squared minus 1, will fix all the points in EFQ squared, we'll send them to 0. And this map, Frobenius cubed minus 1, is going to send all the points of EFQ cubed to 0. So we want to apply this to our random point that we're sampling to kill off the subfield parts. And of course, sorry, I should mention EFQ is a subfield of both of these. So by killing off the EFQ squared part, you're inherently killing off the EFQ part. But right, so we want to apply both of these maps to kill off our subfield parts. But you can notice that these maps kind of have a GCD. The GCD of pi squared minus 1 and pi cubed minus 1 is pi minus 1. And so you don't need to do that twice, so you can simplify. So the map we're going to choose to kill off the subfield part is going to be exactly these multiplied together, divided by their GCD. So we get Frobenius plus 1 times Frobenius cubed minus 1. So putting this together, we are going to sample a random point from our big subfield. We're going to apply our map delta 6 to kill off the subfield part. And now we're going to multiply it by our cofactor to force it into the L torsion group. So this time, because we had more subfields, kind of a nicer structure to EFQ6, we got even more savings because the H6 part is going to be even smaller. And so we save around 2/3 of the multiplications. So not bad. So you kind of see that the amount of savings really depends on how composite K is. Okay, so formalizing this a little bit, this is going to get a bit abstract, but if you understood the examples, I think you're in good shape. But so first we're going to define this map A to K, which is the kth cyclotomic polynomial evaluated at Frobenius. And so we'll use A to K to define our delta. So kind of looking at this numerator, this map is going to send all the points of the extension field to 0. And so we kind of want to get rid of the factors of this that are in the other part. So we only want to be left with the kind of subfield factors that are going to fix the points in the subfields. And so we notice that dividing through by A to K using the cyclotomic polynomial is going to do this. And in particular, we get that the image of delta K is exactly contained in HK. So this delta K is sending us to like our other subgroup like we want it to. Okay. We also have one other trick for when K is even, which is that if you have a point from hk, then its x-coordinate is necessarily going to be over fq to the k over 2. The proof of this is included in the e-prints, but basically, like when k equals 2, we call this the twist trick, because you know when you're working over the twist, it's only the y values that are different from like when you're working over the base field, and the x values are still always contained in the base field. So yeah, this is the same logic is kind of extended for higher choices of k. So now looking at some examples for delta k and how big the size of the leftover subgroup is. You kind of notice, like I said, for very composite numbers like 6, you get more savings. So here you're only doing 2 over 6 amount of the multiplications. So that saves us 2/3. In the case of 8, you're doing 4 over 8 amount of the multiplication. So it's about half savings. Something like 11, you only save about 1 over 11 of the multiplications. So it's not as beneficial, but still something. And then, yeah, in this column, you kind of see what the delta k ends up being. In terms of the scope of the paper, we really focus on these like small-ish choices of k. So we really optimize towards k between 1 to 12. Technically, I mean, I think almost everything is proved in general terms, so you could do it for like much larger k's, but I think most of the benefits are going to be for the small-ish k. So yeah, so in summary, we kind of looked at and focused on how to evaluate these kernel polynomials. We looked at this doubling trick, and then we took that even farther and looked at how we could use those Galois orbits to generate our set S. We looked at how we can compute the kernel generator. And yeah, we have an e-print that will hopefully be out very soon.
Very cool. Thank you for that. Excellent talk. Do we have any questions in the chat, then you are free to type them now. And I see actually we immediately have a question by David Zhao. What are some applications of isogenies over composite field extensions?
Yeah, so things like CRS. So CRS kind of, I haven't read this paper that I mentioned by DeFeo, Smith, and Kiefer. But it definitely has the ability, I shouldn't say definitely, I think composite field extensions are still used in this context. I know L tends to be prime, but I don't think there's any restriction in CRS to having K be prime, unless someone knows something else. But yeah, I know the main focus of this work, like what we had in mind, like I mentioned, was CRS.
Okay, cool. And I think Thomas raised his hand, so I think if he wants to unmute, he can also just ask the question live or type quickly. Yeah. Yep.
Hey, thanks for the nice talk. I was curious if you generated a new CRS curve or not.
No. So we haven't explored really kind of the applications or what the improvements would be, or yeah, for a new CRS curve or the prime. I don't know if this would change, or sorry, not the prime. We haven't started exploring this yet. I'm not sure we'll do it before we publish this paper, but it could be more of a open the future work thing.
Okay, because I'm curious because, well, I'm not exactly sure what the bottleneck is in the field extensions, but if K is composite, then it may be beneficial to try to favor small primes over composite field extensions, I guess, instead of like the 11, although I only think they went up to FP to the ninth in CRS, the last version.
Okay, yeah. I mean, yeah, these like when K is prime for big K, you lose. So it would, like if you could develop a variant of CRS where they focus on these composite field extensions, it would be, you could use this, you'd see better results. For sure.
Well, it would still be CRS. It's just the bottleneck there is finding a curve with a smooth order of points. That's the only thing. So you would need to do a lot of computation.
Yeah,
to find anything.
This paper by like that I keep mentioning kind of did this, and they had, I think they took some months or something to look for such a curve.
Yeah.
And this, yeah, kind of drove Seaside being like, oh, well, if it's super singular, you get this really nice property for free, basically.
Okay.
Yeah.
Yeah, thanks. I have another question, perhaps.
Yeah, go ahead.
Like in the first part, you were talking about splitting the set of P up until L minus 1 times P into two parts, S. So like they also do this in like the Vélu square root formulas, but in a very different way. Is this like in any way compatible, or did you not explore that? Same
No,
question as the chat.
Oh, yeah. No, we haven't explored so much. I do remember reading this paper at some point, but I thought in Vélu square root they took kind of the odd multiples of P.
They only take a square root of them roughly. It maybe very hand wavy now. I think if you have like P, if you have L 101, I think they take like P 10 times P, 20 times P, and so on until 100 times P, and then also all the ones from P until 9P, something like that, and then they like sort of intertwine those in some way using a resultant computation. But I'm hand waving a lot now. So I'm kind of curious if there's something you could do there as well to save some constant factor. Or have you not considered that yet?
No, I mean, I haven't considered that. I can consider it right now.
I was actually thinking about this during the talk too, and what Thomas is mentioning, for the set I, you take multiples of 10 times P essentially, right? So probably the trick applies there as well, but just on a higher level for R
like
defined as 10
extra
times P.
squarings. But then it like when you're choosing kind of have this doubling trick, you really don't get much say over the order in which you put it in order to do the doubling. Like I can say, take X number doublings, but then the ones you get out, you don't have a lot of control over. So then you'd have to like really shape how you're doing kind of these jumps in square root Vélu.
Could be. Then again, if you're only doing it for like specific primes for like a couple hundred at most, you could sort of hard code that for all the ones that are interesting, if it would be possible. Maybe you should ask Ben. He's an author of the Vélu square root paper and also an author of this paper.
Yeah. I mean, he might be, I don't know if he wants to comment. I think he's here, but yeah. If not, yeah, it's something to think about.
Hello. Yeah, I'd say it's definitely, well, something that we've been intending to think about once we get this sorted out. I guess the trick there is in Vélu square root, you want to compute like a square root's worth of the polynomial, let's say, and then do multi-point evaluation on that. What would be interesting here would be to work out if somehow, well, I guess when you're doing Vélu square root, you can just take like P, 2P, 3P, whatever, like build up that piece of the polynomial, and there's a very sort of simple addition chain to work out all those multiples of P. The question is how you can get that to interact nicely with the Galois orbits. I'm sure there is an interesting interaction. It's then a question of how much of that speed up transfers easily or with difficulty or what. Either way, you're going to end up using chunk more memory, doing a bunch of interesting things. I'm not really speaking like Daft Punk, but let's say that this noise cancelling headphones is enhancing the noise rather than cancelling it behind me. So I hope this is improving the ambiance of your afternoons wherever you are, and bringing a bit more like dubious groove to the isogeny party. There you go. Anyway, yeah, something to check out there.
Okay, cool. Thanks for the comments.
Yeah, so I think it would probably depend a lot also on L. But if you are often using the same L, maybe it would be worth like hard coding. Yeah. And then I saw this other question from David. Let me go back to this table.
let me repeat it for people that will watch the recording. David asks, do you get more relative savings from extension degrees with repeated factors, for example, 12, or distinct factors, for example, 30?
So maybe comparing something like 9 and 12, or even 8 and 12. I think 10 and 12. I would guess, I mean, we don't have a kind of a small sample size, but my first initial guess would be that the distinct factors are going to go farther because you're going to get kind of better subfield behaviors. So looking at this little table, you're going to have more of these like maps going into delta. Whereas when you have repeated factors, because kind of you're only multiplying through by the, dividing through by the GCD, you basically are doing less in this delta and more in the multiplications. If that makes sense. Okay. And
then Alexei follows up with, is it Euler phi k over k, the cost ratio?
Yes. Yeah, I thought about adding that. Ben suggested I add it to the table, but I think it just slipped my mind. What a good way.
And then another follow-up question is, what are good ways of computing the Frobenius map? Raising to the qth power sounds slower than, for example, doubling.
Yeah, so this depends on kind of your field, the way you want to represent field arithmetic. So there are representations where Frobenius will be extremely cheap, almost for free. And then there are ways where maybe you're optimizing to something else where it'll be basically equivalent to just qth powering. You can go between these field representations as well. Of course, each time you switch field representations, this is also going to have a cost associated to it. But in general, there are ways to make Frobenius quite attractive, let's say.
Could you also maybe pre-compute the Frobenius action if you work over a fixed field? Does it work like on the generators?
Sorry, going back to the slide. Because like you're dealing with different alpha, I'm not sure. Is this the slide you're referring to?
No, I was just also thinking, no, sorry, it's just the Alexis question with what are the good ways to compute the Frobenius maps? Maybe it was nonsensical, sorry.
Oh, no, well, like just thinking about it, I feel like because your input is changing, the pre-computation would be tough. If you choose to use the eigenvalue, you can like pre-compute these powers of lambda, but I'm not sure that really, I would guess that's not really the bottleneck anyway.
And then I'll still have another question, which might be the last one if nobody else comes up in the chat. You compared this for different curve models at some slide. Did you check it actually? Do you also in the paper check it for like a lot of curve models? Because I could imagine that Montgomery is the best for doubling probably, but I'm not 100% sure. And here you really want to shift everything to doubling, I guess.
Yeah, I guess. And so your question is like, is it worth like looking at other curve models?
Yeah.
Yeah, so it no matter what, I would guess it's always going to be the best choice to stick with whatever model you're using in the system. And then depending on what that model is, see what the savings would be. It'll change for each model. Regardless, I think in all the instances I can think of, doubling will always be faster than addition. Maybe that's a bold claim, but in many instances at least. So you should always get some amount of improvements, but yeah, using something like Montgomery will probably give more improvements. But to do something like, if you're working in something that's already a short wire stress, I don't think it would ever be worth it to like quickly convert to Montgomery to do the doublings and then convert back. So yeah, the model you choose will have a big effect on whether this would be worth it or not.
Cool. Then I think we don't have any other questions left, and otherwise somebody should raise their hand or quickly type something in the chat. But if not, I want to thank you again for a very excellent talk. I enjoyed it a lot. And I want to once again repeat the thing that Jonathan said, that we will not have a session in 2 weeks because there is Eurocrypt, at which we have the affiliated event where we do the brainstorm session. And we still hope for a lot of good ideas to have there for the brainstorm session. And if you still want to hang out a bit after the talk, just turn on your camera, turn on your mic, and join us in a little chat. Also, if you have any questions on Eurocrypt, I guess.